Hi, thanks for joining me today for my OpenMP booth talk on low-cost algorithmic strategies for HPC that are auto-tuned with the focus on OpenMP. I'm Vivek Kale, and I'm a senior computer scientist at Sandia National Laboratories. This is a motivating example code structure for a DOE simulation that's running on a cluster of SMPs. And this is the typical code structure that many of the applications take. It basically uses inside the core part is here in this code is this threaded computation region with this pragma parallel 4 and then outside of that, there is a bulk synchronous parallel time-stepping loop that basically runs this simulation or an iterative solver multiple times. And so, and note that we have then within that BSB time-stepping loop, this MPI-XN receive wait all. So these are loosely synchronous MPI communications, and you can have interleavings of computation communication within each time step. And then you also have this OpenMP parallel loop with a this static schedule, and in that you have this team threads and teams share this variables, the u and u new. So this is typical code, and what we need to do is assess then the ease of use or performance portability, how correct this code is. So that might include numerical accuracy. And then we also need the efficiency. So performance meaning execution time, bandwidth, flops, and then joules per how much energy per second. And so with this code, there's a lot of different things coming into play in HPC, and I'd like to just highlight one of the issues here, and that is the problem of amplification. Here on the left at the top, you'll see that you have each node represented in the blue, and then these red bars are the cores. Within each node there's the parallel region running the stencil OpenMP, and then they're doing the border exchange, and then either global reduce or global reduce or nothing. But either way, there's some sort of synchronization that has to happen. And so now you see these extended bars. This actually, if you consider an all reduce here, just one node gets perturbed, then everyone gets perturbed. Basically, it gets slowed down. So noise delays every time step on some node, and and so as you scale to a large number of nodes, that probability of noise occurring it becomes the constant addition with the number of time steps. So scaling is therefore, as shown by previous work, is not good due to this amplification. Now, the way to fix this is to redistribute work within each node. And so within each node, if we could find a perfect distribution, you see now that this load imbalance, this delay is basically reduced. The question is then, how do we redistribute the work efficiently? So the answer is that we should consider two different parameters here. That's the cost or idle time due to the load imbalance and the cost due to the movement or migration of work from the load balancing. And so if you consider a static and OpenMP dynamic schedules, both address those each cost differently. Obviously, a dynamic schedule will incur lots of scheduling overhead, not just due to DQ, that is adjusting chunk size, but also just the data locality overhead. And chunk size can help, but what we argue is that I as done in my dissertation work, a mixed static dynamic schedule where threads first do some pre-assigned work statically and then immediately go on to do the remaining chunks of work dynamically is the best. And this, the amount of work done statically or the number of iterations that are statically assigned should be a parameter. And so what is the code look like? Well, here's the code transformation. So we can enhance this with data layout and loop transformations. Specifically, we have in the original code we showed in the last slide. Threads are first assigned iterations like this, these pre-assigned static iterations, but then you'll see that thread 2 has to jump all the way here after it finishes its last iteration. That disturbs spatial locality, and so how can this be fixed? Well, we can stagger these iterations and then thread so that each thread has does its static work and then immediately starts some dynamic work that it's assigned. So it uses stealing queues, per thread stealing queues, and then it pulls threads. And then if it doesn't have any work, then it steals from another thread's queue here. And so this improves spatial locality, and we note that other loop transformations can be composed. I'll also note that we have locality optimizations for tasking in OpenMP, which is the in particular task loop. And we have done some experiments that show how a 2D Jacobi and generalized matrix multiplication both have both improve in their performance when we add locality hints to constrain the data movement across cores. So for the scheduling strategies we showed before, we're actually here optimizing temporal locality. And so we remember where each chunk ran, meaning which thread each chunk ran on in the previous time step, and then try to dequeue that chunk onto the same thread in this time step. And so more efficient data movement here showed not just lower execution time because of more data going, not having to go through the DRAM. It also showed lower energy consumption. We measured joules here. This is for an Intel 24-core Xeon. So far, we just talked about clusters of SMPs. But what about clusters with nodes having heterogeneous nodes? Nodes having heterogeneity. So, in that case, we need to modify our dynamic scheduling and mixed static low-cost schedules a bit. And this involves using the task loop and a specific assignment mechanism of a task of that task loop to a GPU. Now, the task loop task consists of several target regions, and those target regions use the device clause to identify which device that the target region should be offloaded to. Essentially, this whole colored piece is a device task, and each device task has 3 CPU side subtasks. It has a pre-task to choose the device, a task to fire a GPU kernel, and a post-task to deal with the completion of task and release work. You should note that not every strategy needs all 3. And so by doing this, we can we can also tune the grain size to have more tasks, more target regions within the task loop be offloaded all at once to a GPU. And this helps to reduce some overhead in terms of having to handle different thread contexts. And this is one way to get low cost. And we also can do other adaptive load balancing schemes. And we did this study through the paper shown here on addressing load imbalance across multi-GPU systems, and we focused on bioinformatics applications. Here's how this would work using in application code. And here, this is where a user-defined multi-GPU schedule is really important, because what does it mean for a schedule across multiple GPUs to be dynamic? It could be on the CPU side static, GPU side dynamic, or vice versa. So it's important to extend the declare schedule with a level, and that level identifies the level of parallelism that the schedule operates on. And there's an optional type or a modifier which that could be the kind of the scheduling, but again, this is optional. And so now with this, we see that multiple threads here are executing in parallel, and they're then offloading work to one of the several GPUs. The way that they're offloading work to any one of the several GPUs is through this spread clause. And spread, what it will do is pick or take some particular set of devices, and then each thread will offload based on the schedule to that particular device. Here we consider unified shared memory for sake of simplicity, and also, again, the target spread clause will likely not be in the specification for 6.0. It will probably be itself a level of parallelism or a level of work sharing itself. You might in fact see that teams distribute have different have a different syntax associated with it in 6.0, but this is unofficial. We then experiment with different locality strengths, and so we basically tune that dynamic fraction. Here, the dynamic fraction has to be a probability of picking a GPU with a static adaptive scheduling instead of a purely static scheduling. And we use this probability rather than picking using the strategy described earlier for multi-cores, because we can't use in OpenMP currently an event-based trigger which allows a child task on the GPU to tell its parent task on the CPU that the GPU is ready for more work. And so we use this this methodology, and we run it with Summit, and we run with randomized matrix multiplication, so a load and balance code, and a load balance code stencil, which we showed earlier. And we see basically that the dynamic fraction is different for these two applications, and the optimal dynamic fraction shown here is for load and balance code is about 0.8. Optimal dynamic fraction for the stencil is 0.1. So this mixed static dynamic is beneficial for both locality and thread to device affinity. We also did some work with tunable low-cost asynchronous offloading, and here the problem is when you're using the Clangs LLVM OpenMP, the register file usage is high, and using it specifically for the asynchronous offload for Floyd-Warshall. Our hypothesis is to reduce the overhead of the asynchronous offloading through minimizing thread state. So we actually explicitly use the LLVM option FOpenMP no thread state. And then we tune the GPU parallelization parameters of thread limit and num threads and other parameters. And what we saw is basically, once we did this, the performance now came of Clang LLVM now came close to CUDA's corresponding asynchronous offloading. And there's a paper here. I've worked with the expansion and extension of this work to address multi-level load balancing. Essentially, there's two aspects to this. One, how does the load balancing across node, or maybe a set of topologically near nodes, get impacted by this low-cost loop scheduling within each node? We should to do this, I considered the Charm++ runtime system as the one for the intranode load balancing, and then inserted into a specific library called CK-Loop the hybrid static dynamic scheduling. And what we saw is that you need this when we tune the parameters of periodicity of Charm++, along with the static fraction, we improve performance for our particle and cell code significantly. And this is code in the GitHub repo shown. The other aspect is tuning the dynamic fraction just based on the MPI slack. And this is where basically if the MPI processes are not load balancing, are not doing load balancing, but there is load imbalance across the MPI processes, how does this dynamic fraction adjust? So this actually can be coupled with the previous work by considering each topologically close set of nodes as one supernode. And so now what are the dynamic fractions of those of the cards within each of those within each supernode? So that can be identified. So the supernode can be associated with an MPI process, and then you can have basically a formula that optimizes for DQ overhead and load imbalance. We point out that we do a code transformation on our original codes to use this /conscious runtime and our loop, our low overhead loop scheduling. So you can just take a bare OpenMP code, MPI and OpenMP code, and then transform it to have this slack conscious and potential, and also inter-node load balance, interoperable load balancing and loop scheduling within it. And so what you can do, what we show here is basically consider the charm MPI operating over topologically close nodes, and then across nodes using MPI. And so essentially this for loop this region is handled by charm++ and the CK loop, and then outside it's basically the MPI. And so predict dynamics fraction calls a library called slacktrace, which is basically a Python wrapper across PM for which generates new PMPI code. And then this here we have a vsched init and vsched finalize, so that's the lightweight scheduling. We need to consider the ease of use, really, of the programmer. So we do have we have the MPI plus OpenMP code. Some people that is short enough, reasonable enough. But for performance portability, for other reasons, what if you could just write the algorithm, the core unparalleled algorithm, and then just stick it in as a functor or a lambda, and the policies and the patterns that you apply are kind of separate. They're separated out. And this is what is kind of the theme of Raja and Cocos, and basically having a C++ parallel standard template library. And it's basically that so with our strategy, it's basically we actually are adding a new lightweight scheduling policy, or OMP LWS in Raja. And there's so this is passed into the Raja for all, and then the range segments are specified here. So putting this together, we have a way now to identify and represent low-cost strategies in OpenMP within performance portable library of Raja. And so now, how can we really make use of this and kind of tune these low-cost strategies within Raja? So, if we remember, there's the user-defined schedules. There are multi-XP schedules, and there's asynchronous offloading. All of these can be kind of brought up into the Raja library, and built within the library. They can also, within the library, be automatically generated, perhaps through a machine learning agent. So you could actually visualize some machine generating these new loop scheduling strategies through that user-defined scheduling interface. And once it does that, then it will tune the parameters that it's created for that loop schedule. And so this is a really exciting thing, actually, if to bring in some sort of machine-generated HPC performance optimization strategies within a library like Raja, and potentially not just work within Node, but if Raja and Cocos kind of use C++ as both within and across Node, perhaps integrating MPIs and Charm MPIs implementation, this would provide a very powerful mechanism to not just get portable code, but performance portable code in applications. So, in conclusion, I'd like to point out that there's a problem that HPC software tuning a parameter for one particular dimension can incur cost with that dimension or in another dimension. For solving this, we can consider these auto-tuned, low-cost algorithmic strategies. And in this talk, I focused on LLVM's OpenMP. And so there's different ways that we looked at doing this. I showed the intranode support, which is the core support, and that's for the multi-cores and multi-XPUs. And then I showed with just multi-XPU, I showed this tuned low-cost asynchronous offloading. Loop schedules and asynchronous offloading in OpenMP are the core strategies within Node, and internode support involves this multi-level load balancing, and we considered how to have these integration with the Charm++ load balancers, and then have these slack conscious scheduling for adjusting dynamic fraction across topologically near Charm++ logical nodes. So then we talked about how to make these strategies performance portable and intelligently auto-tuned, particularly talking about the OpenMP user-defined schedules and C++ integration. And we talked about the rows source-to-source transformations for the injection of runtime support, and finally the ongoing efforts, which I am very excited about, is basically an AI-enabled auto-tuning with Raja's and Cocos's Apollo and Caliper. So for future work, we're planning to expand the dimensions to consider not just the performance so much, but much more on the effectiveness, so the correctness, and that includes reproducibility and numerical accuracy. So we're tuning for those in addition to perform the dimension of performance. And then I plan to do projections through architectural simulators, projections of scalability of my approach. Log GeoPSim, it's a simulator written by Torsten Hoefler. This was for noise, but it can actually be extended through to identify how loop schedules work within each local operation. So the cost model. And then finally, plan to look into strategies of that I described, but for the area of AI/ML and the cloud platform. Thank you for joining me.